I want to start off by reminding us that, because I think this was David who was talking about it as he was leaving mechanics today. Why are there so many different right-hand rules? There's not. There's a right-hand rule. And it's not intended to be difficult to understand, or it's not intended to be convoluted. This is the way nature works. So when we talk about the fact that I have a free particle traveling through space with some velocity, and say it's a positive charge, if there's a region of space with a magnetic field, people over the course of years and years and years of observing saw that the particle, as it traveled through space, curved to the left. So they didn't say, wow, it must be obeying the right-hand rule. They figured out that its motion through the magnetic field caused a force on the particle. And they probably looked for ways that they could help remember this. How would I be able to predict when the next particle comes, what direction it's going to curve? Why the right hand? Probably because they had it handy. Get it? Handy, see, huh? That's probably what. I don't really know. I've never looked it up to see why did they choose to do it this way. Probably the same reason why you guys still remember some of your mnemonics. Once you remember something with a mnemonic, it's easy to probably, keep it in the back of your brain. Who knows the mnemonic for like kingdom, phylum?
Big Kiko, come over for Greek salad.
Okay, see? Point proven. Now, there are more formulations of the right-hand rule, not because there are different versions of the right-hand rule, but because there's different things that have to do with the manipulation of a vector product. So we've been looking at one aspect of the vector product. In the case of this problem, it's, we're looking at the size of the force. There are other aspects of vector products that produce different results. And so there's different ways to apply the cross product. So although we are going to see that there's another version of the right-hand rule actually quite soon, it's really not different than this. In the case of these problems, we're looking at the direction of the force based on the creation of a plane due to the two vectors that describe the velocity and the magnetic field. In a couple, 3 days, we're going to be figuring out where the magnetic field comes from. And that's going to involve a different right-hand rule, but it's still a cross product. It's just a different formulation of that cross product. We're seeing the cross product solved in this way. There's another way in which the cross product can be reorganized. So this isn't, I'm not trying to confuse you, but those of you who are in mechanics, we're going to be talking about right-hand rule for rotational motion and the definition of the rotational vector. Well, that uses the other formulation of the cross product. I'm sorry, the other formulation of the right-hand rule, and will lead to other formulations of the cross product, torque and things like that. And here, the magnetic field is circular. What's one way to describe that? The curl of your fingers. So why is it a right-hand rule? Because it works well and it's still consistent. The right hand can still be used to predict direction. So don't make it more complicated than it is. But yes, you're going to be doing some weird gang signs on your test, I am sure. So, and we haven't even gotten into some of the more interesting things. So get that out of the way. We're going to talk right now about the force on a current carrying wire, which is what we were talking about right at the end of class period last week. So let's remind ourselves what I had written last week. So magnetic field. Nope, we finished Hall effect. Good times, Hall effect. But nope. So if I have a wire that I place in a region of space where there is a magnetic field, and I allow a current to flow through that wire. Now, when we talk about current here, we are talking about the flow of positive particles, conventional current. And although the force on the current carrying wire won't matter if you're dealing with positive flow or negative flow, you should remember that from this point forward, even though we talked about the Hall effect being a method for determining what's actually moving in the wire, we always assume current flow refers to the flow of positively charged particles. All of our conventions are based on that idea. So in this case, we assume that there are a large number of positive particles all moving in the direction of the conventional current. Now, as those particles move through the wire, they each individually experience a force. And the force on all of those particles is to the left. However, the particles are constrained to move in the wire. These are not free particles. These are particles that are stuck inside the wire. They can't leave the wire, which means all those particles experience a force which presses on the structure of the wire, causing a generalized force on the wire to the left. It can be shown through our definition of current, which is just the rate of flow of charged particles. It can be shown through our definition of current that the force on the current carrying wire is equal to I L cross B. Now, some of these variables I think are obvious. I is going to be the current. B is going to be the mag field. However, L may not be obvious. L is the length of wire subjected to the magnetic field. It's not the length of wire. It's the length of wire subjected to the magnetic field. So in the case of this problem, L would be only this portion of the length. This portion of the length is what's subjected to the magnetic field. Therefore, that portion of the wire would experience this force. Now, there are a couple of caveats here, but let's hit the high points. First, this is a generalized force that exists all over the surface of the wire. It's not applied in one place. So the entire length of the wire that is subjected to this magnetic field is experiencing a generalized force that's given by this calculation. But it's not concentrated in one place on the wire. It's distributed throughout the entire wire that's subjected to the magnetic field. There's some usefulness there. It means that if you're going to use the magnetic force, you get the convenience of understanding that your object isn't going to necessarily collapse under the application of this force, since that force is spread out through the whole thing. It's like the gravitational force. Although we say it acts at your center of mass, the truth is it acts generally over your entire body. So if you jump from a building, it's not like suddenly your head gets pulled more than the rest of your body. Your head and your entire body experience a generalized force. The entire force equivalent to your weight. Same idea here. This force is distributed over the entire length of the wire that is subjected to the magnetic field. The total force is here. You could conceivably calculate a force per unit length and figure out how much each contribution of the force is along the entire length of the wire. That's generally not necessary for our purposes. This force is different than the force on a free charge. The wire dictates the direction of motion of the charge. Current is not a vector quantity. We tend to think of it as a vector quantity, but it's not. Current is not a vector quantity. The length of the wire is a vector quantity. So we take the vector portion from the length of the wire, the shape of the wire. So technically, we could bend the wire into any shape we want, and it could experience this force. More importantly, since the charged particles are forced to move through the wire, they cause a generalized force to the wire, which will cause the wire to perhaps shift position. Unlike the force on a free charge, the force on a current carrying wire can start the wire into motion and could stop the wire's motion. This is different than what we said before. Because the wire forces our particles to be constrained, we can use this arrangement to start the wire into motion or to stop the wire from moving. Let me demonstrate an example. Imagine I have two solid metal rails. So two pieces of metal. This could be like the rails of a stapler if you want. Just two pieces of metal that are separated in space and are not in contact with each other. And let's say I place them in a region of space where there is a magnetic field pointed out of the board towards you. Let's connect the two rails with a potential difference. So I bring the rails up to a potential difference. And yeah, that should do. Now, right now, nothing would happen. There's no flow of charged particles. I didn't say that these were plates. I just said they were rails. So they might not have any capacitance in which there's a flow of charged particles. They've just been separated by a potential difference. So right now, nothing's happening. But let's say I have a bar that I could just drop onto the rails right here. The moment the bar is dropped onto the rails, I complete a circuit. I provide a pathway for charges to move, and therefore I'll have a current generated. The way I've drawn this, the current would be that way in the circuit. The moment the bar strikes the two rails, I will get a generalized force acting all along the red piece of metal, the bar. And I'm pretty confident that you guys can use your right-hand rule to figure out that the bar is going to be pressed to the right. We in agreement? So the bar experiences a force. That's going to cause the bar to begin to move to the right. I can experience that force throughout the entire length, but the bar is in contact with the rails and inside this magnetic field. The size of that force will stay constant as long as the current stays constant. Now, of course, at the same time, wherever the bar is, there's also a length of portion of the bar, a length of the portion of the rail that has a current in it too. So realize that there's now current traveling this way in the top rail and this way in the bottom rail. That's also going to create a force on the top and bottom rail. So I would have to probably ensure that they are constrained in place so they don't move. Otherwise, they would also move. But if the bar was free to move, I could use this to launch the bar off the edge of the rails. This is the definition of a railgun. And although the Navy's been attempting to try and make railguns for years, this is the basic hypothesis of how a railgun would operate. There's lots of advantages to a propulsion system like this. And we've tried several different methods for trying to make a propulsion system like this work. One of the things that's great about it is that once you establish this, there's no explosion. Right? There's no detonation of some kind of accelerant that would push this thing out of a barrel. Also, the whole system could be exposed if I wanted to. It doesn't have to be contained in an area where there's a vacuum or an area where I contain a pressure system where expanding gas is going to push my thing out. Next, as gas expands, the actual force on the projectile gets smaller. In this case, the force on my projectile is going to stay uniform the whole time it's along the chamber. More importantly, and this might not be obvious to you, you can launch more than one at once. As long as I can maintain the potential difference between the rails, I can have lots of these things going at one time. Railguns have several advantages. There are significant disadvantages, which is why they don't work. So although you could build one of these, you probably can't attain the kind of velocity that you want to have. Some of the disadvantages, I think, are obvious. We really would prefer not to launch our projectile in such a way that it's oriented this way to its motion of travel. Now, you can make the projectile smaller by getting the rails closer together, and therefore it doesn't have to be that way. But remember, diminishing returns. If we make our projectile smaller, we reduce how much force we get on the projectile itself. We need to have enough length that is impingent on the magnetic field for there to be a reasonable enough force to cause it to accelerate. The other problem with this as a way of launching projectiles is you have to maintain that magnetic field all along the length of your barrel. The Navy has been testing this kind of railgun weapon for years. Part of the reason is because naval vessels have access to almost unlimited electricity. You have a nuclear power plant, you can generate a lot of electricity. And therefore, they can generate the kind of electricity necessary to be able to generate the magnetic fields that are required here. To make them work, though, you generally have to operate them in a vacuum. Having too much air inside the barrel makes it kind of a diminishing proposition. And you also have to have a way of delivering your round to the rails in such a way that you don't also damage the people in the system who might be exposed to a very high magnetic field. So railguns in general have not been particularly effective as a means of firing projectiles. That doesn't mean that you won't discover a way to make them great. You could make a cheap, easy railgun with just staples and an old taken apart stapler. Right? It doesn't take very much. A stapler's got a couple of rails, and staples are nice and light. You already have the dimensions to set one up because the stapler and the staples all fit together. You'll find it doesn't work as nicely as you'd like, but I always have a couple students who are trying to find a way to make a railgun because they think that they're really neat sounding until they actually realize that they're not easy to actually get to construct. But try it. Our 6-volt batteries and a standard swing line stapler, you can make a poor man's railgun. It'll shoot the staples. Not particularly fast. But if you've never made one before, you should try it. Can't hurt, right? Well, can't hurt much, right? Although you'll probably find that just squeezing the stapler will probably launch the staplers faster. Yes, David. I feared you'd have a question. What's that?
The Cheetah Hunt uses a railgun to launch you, basically?
No. This system, I mean, as you're describing it, you're right. This could be the kind of system that could be used for propulsion of like Cheetah Hunt. And yes, there are several roller coasters that use this kind of propulsion system for pushing like roller coaster vehicles. The Cheetah Hunt system is a magnetic system, but there's other ways to utilize this that are somewhat more effective. The system used by Cheetah Hunt's a little different than this, and we'll talk about it. Yes, sir.
The staples have to be non-magnetic.
Well, that's part of the problem, yeah. Is that the staples will be attracted to the magnetic field because they're made out of cheap metal. You can usually generally get the force on them from the current to be greater than the force in the magnetic field, though. So they will move across the rails. You have to lubricate the rails, though. And you have to lubricate it with something that still conducts electricity. and that'll be enough for it to be able to slide. It's not great. I told you, it barely works.
I was just thinking, I didn't have any plans building one. Like just looking at it, I would think like a bar would be attracted into the rails.
It will be.
That's it.
So, when they do this for like the Navy, one way to prevent that is by using a non-paramagnetic metal, like aluminum or something. That will work. Your actual staples will be ineffective or less effective because they are attracted to a magnet. So you have to find a metal, something that's conducting that isn't easily attracted to a magnet. Most aluminum does that, so it's pretty easy to use aluminum. So if we were to build one out of a stapler, there will be some disappointment. Now, Cheetah Hunt uses a different effect entirely, which we'll go into. But there is something here that I want to also remember to call your attention to. And again, it's not obvious, but we're applying a force to this piece of metal through the action of electric current. And if it's not clear to you where I'm going with this, we're generating mechanical energy directly from electrical energy. We can't get something for nothing here, but we're going to have to begin to understand that the ability to generate mechanical motion from an electric circuit is probably one of the most far-reaching inventions of the late 19th century, early 20th century. The electric motor revolutionizes almost all of the human condition. I would say one of the biggest revolutions in your life and mine was the cell phone, but in your grandparents' life and my grandparents' life, it was the electrical motor. The ability to just flip a switch and have motion didn't exist until about the late 19th century. Electric motors revolutionized how we do all sorts of things. I want you to consider all the different electric motors you probably interacted with in just coming to class today. It's probably in the hundreds because we use them to do so many things. Anybody have electric door locks on their cars? Push the button on the remote and the door locks close. Again, you're converting electrical energy into mechanical energy. Did you crank over your car or did electric motor start your car? Because we didn't always have cars that could be started with a turn of a key. You had to turn the throttle on, go out front, and get the engine turning yourself with a crank, then pull the crank out before it ripped your arm off, put it in the back seat of the car, and drive away. Nowadays, we wouldn't do that. How do you like those windshield wipers? They work pretty well here in Florida. Do you have a fan in your car? One that will blow air across you? I mean, you start thinking of all the little places where we have used electrical energy to generate mechanical energy, begins to boggle the mind. Anybody nuke their lunch here today? That rotating platform didn't rotate on its own. And inside that little device that makes everything get hot magically, we've got like 5 or 6 motors. There's one that's moving the element around to uniformly cook your food. There's also the one that's getting the fan around to cool the element to make sure it doesn't overheat inside there. It's amazing the number of places we've put small, simple electric motors. But the capacity to generate motion from an electric current is a revolutionary idea. This is the least interesting way to do it. Because although it will maybe fire a slug across the edge of the rails, the idea that we could get some kind of reciprocating motion, meaning something that you could use in a reciprocating fashion that continuously operates, is much more interesting. So although we will look at a couple different kinds of motors, this represents the first conversion of electrical energy to mechanical energy that we've been able to discuss. So one of the things that is going to be a part of our conversation over the next couple of weeks is to be able to determine how much electrical energy can be converted to mechanical work. In this example alone, the information I've given you hasn't been sufficient to do so, but there's a potential difference here, which generates a current, which means we know the power of this system is going to be related to the voltage and the current. And we know that power is also the work done over time. starting from here, we can figure out how much electrical work must have been done on the projectile as it was pushed along the rails. From there, we should be able to determine work done, change in kinetic energy. We also have a system where there's a constant force, so we're talking about a constant acceleration. Lots of pieces between kinematics and electricity. And the beautiful thing is if you just put a switch in here, you can turn it on and off. So, beginning of the year, let's talk about a simple way to make a reciprocating motor. First, I want to consider the shape of our motor. I would not build it this way, but it's easier to understand the shape of this motor. So I'm going to take a piece of wire and bend it into a rectangular shape. Trying to be careful here to make the part where the wire comes into the center near the center of my rectangle, so that kind of has a shape like that. So this is my rectangular motor core. And in this motor core, if I send a current in this way, then obviously we'll have the current traveling this way, this way, this way, this way, and then this way, and we receive the current there. So we're generating what I would say is a current loop. Does that make sense? So pull those arrows out. I'm going to surround this with a magnetic field. Now, it's hard to see this the way I'm going to draw it, so I'm going to draw it more than one way. So here's the first way. I'm going to have a magnetic field. All right, so I'm going to pause this here. We'll pick this back up on